and 25 minutes plus 5 for question. And to you, the word.
Okay, thank you very much. I'd like to start apologizing for not being able to be there with you, but last week was a little bit tough to me. I got sick. I'm not fully recovered yet, but I expect to be able to make this talk smoothly. And if I'm maybe we'll be interrupted by some coughing, but I try to do my best. So I'm going to talk about a recent work that I did in collaboration with some people from the York University, and it's attempted to be quite applied work. So I would like to start make some advertisement because I'm from Federal University of Viçosa. Maybe many of you doesn't know this university because it's based in Minas Gerais. His tradition is more in agricultural science, but we have a big group of complex systems. And here is our group. It's a picture that we took last year. Not all these members are still with us. Some of them are alumni, but at least four of these individuals are there with you. Iago, Fabio, Lucio, who are students from Argentina that they are spending some time with us, and Hugo, who are probably in this audience. My talk will be divided essentially in four parts. I will do a very brief introduction and then explain the model that I'm going to explore and some application for vaccines and conclude very quickly with some remarks. Um, so I'll start to talking very briefly about rumor spreading on networks, and it gives only a few ingredients that I'm going to use in this talk. But the motivation for this kind of problem is uh, obvious. Yeah, we are facing problems about polarization all around the world. I'm giving here examples of politics, but it's not only the case. We have very different issues where um, the spreading of information are shaping the world that we live, the way how we interact, the way how we respond to situations. And what is contrary this kind of behavior uh, is spreading of information that are not necessarily good information. All the fake news are really a very modern problem that we have to keep in control. And there is a lot of power. There's a lot of interest behind this, and very important people that has some, how to say, plans for the world that involving controlling the way that information is spread and how information reaches people. So I've given here two very important examples, but we have many others. So to understand how information spread and how this impacts our lives is a really important issue. And here in Brazil, for example, people use the internet to get informed about everything. So here I have some charts that explain the main reason why people use internet here in Brazil. It is not different for other places in the world. How can you see here 8% of the individuals using the information to get the internet to get informed? So uh, to know how this information spreads is really a central aspect. I'm going to tell to you one example um, that we investigated a few years ago that we have one thing called echo chamber effect. The echo chamber effect, maybe some of you are aware about it, but it refers when individuals are talking to a community that has more or less the same thinking about some issue. So we can quantify these effects that we can you when you stay speaking with people that think more or less like you, and you can apply these to some polarized situations that form communities. Here is one example important for Brazil. a few years ago, more than 10 years ago, we have an impeachment process that was motivated by discussions in the society, including the formation of echo chambers. So you can, for example, characterize these discussions looking for social networks. Here we investigated um, how this discussion happened in Twitter. So we have two communities. We observed two communities at that time. One community that was against the impeachment, and another community that was supported the impeachment. And you can characterize how the flux of information goes from one community to another. And interestingly, we can see that the capacity to spread the information is not uniform. Despite of the two communities that we identified here are, are very similar size and properties, the capacity to spread is different. So in this case, here we show a measure of the capacity to spread the information is called spreadability. From one community to the other, you can see that these blue communities, that those that support the impeachment, are much more effective to spread information. So you can investigate information spreading on networks and try to understand this better. Um, so the point that is going to present here is a little bit different because I'm going to try to join information and epidemic spreading. If you want to follow some details about these works, he was published a few months ago. It's a collaboration with the York University, mainly with Nancy Kondichi, whose name in our beauty friend is Nancy. He was the PhD student who conducted this work, and Sayed Moghades, and also with the help of the motivation. Sorry, the motivation for this work is the following. Imagine that you have some information. For example, here I'm telling about the COVID times when people were incentivized or not to wear face masks. And then this information feed some online social networks, and this shapes the behaviors of individuals in the society. For example, here we can see some individuals who are not wearing a mask and others who are uh, taking this protection. And then you interact with your friends. So you have different networks here, information network, what I will call of cognition networks, that the networks of your surroundings and your interaction, social network, when the spreading phenomenon can happen. So um, idea here is to tackle this problem considering a multi-layer structure. When you have different networks that comprise the same individuals, but the connections are independent. So I'm going to talk about epidemic spreading. It's a very popular issue. So just to remember very briefly that epidemics usually we consider the basic states. For example, here I'm telling about the basic models like susceptible, infected, and recovered. Recovered he maybe you were removed from the network, or you have some immunization, or you can have many different other aspects. I will focus only in the simple dynamics, consider the SIR model here. But information spreading was long ago identified to be very similar to epidemic spreading. So you can make some parallel between the infection transmission with the transmission of rumors. For example, the susceptible individuals plays the roles of the ignorant individuals that are not aware about some rumor. And the infectious individuals are similar to the spreaders, and the removed individuals or the recovered individuals are similar to the stifler individuals that are aware about the rumor but are not interested anymore. This is a very classical work that was proposed in the 60s by Dylan Kendall. It's a very short paper published in Nature, one-page paper, very interesting insight. But a little bit later, Mackey and Thompson realized that while the information spreading is very similar to the infection spreading because they are due to contact between an ignorant and a spreader. The stifling process is a little bit different because you stop spreading some issue only after you are saturated. Your capacity to transmit is saturated. You cannot transmit anymore. So the stifling process also depends on the contacts with individuals who are aware about that rumor. So it's not spontaneous how happens in the case of an infection process. Well, the basic model that tried to couple information and epidemic spreading was proposed more than 10 years ago with a group from Alex Arenas from Tarragona. And the idea there was to use two layers, a network with two layers, one for the contact, physical contact for disease spread, and another one for the information spread. Here, this UAU model is unaware, aware, and unaware model. In the bottom layer, we have a SIS model, that's the standard one. You can see that the information spread impacts the capacity to the epidemic to spread. Here in the abscissa, we have the epidemic threshold. You can see that depending on the infection spread, the epidemic threshold can increase. So if you spread the information more, in this case, it's not misinformation, is a warning about the risk of some epidemics. If you spread more efficiently, you can raise the epidemic threshold and then reduce the capacity of the infection to spread. And this type of work became very popular. There is at least 100 citations every year with many bifurcations or with many modifications of this process published essentially every week. Well, but there is another ways to approach the information spreading. In this school, in this conference, we are telling about higher order networks. We can have group interactions. For example, here you have some cliques now depicting some groups that are interacting. But this is different from the higher order interactions. So the idea of group interactions is that you can model these interactions differently from the decomposition of many pairwise interactions. So I'm assuming here that after 1 week in this school, you have learned about this, and I will pass very quickly through this issue. And but the idea of this works is to include this kind of group interactions for the information spread and see how it impacts in the epidemic dissemination. So I present here a summary of the model that I'm going to present to you. I have a multi-layer structure. One that we have one layer for information diffusion. In this information diffusion layer, we have a higher order network of interactions. And in this network, I have rumor spreading happens. This rumor spreading is very similar to the Mac-Thompson process. When you have unaware individual who are ignorant, we have the gossipers that are spreading the information. You have the aware individuals that are stiflers or not, depending on the interpretation. In this case, they are not spreading anymore, but they can go back to the unaware compartment because they can just become interested in the issue again because we have some alteration or because they simply do not remember about the details. We have other features. For example, we have a correction of the gossipers. I will explain this in more detail soon. And you will also have a relapse time when you stay after some time individuals that were corrected become again uh, uh, stifler in this dynamic. We have a second layer that we're calling cognition layer. That means that environment that you see, your neighborhood. And this network, we are assuming that they are a pairwise network. A pairwise network uh, with a random connections. We're represented here with a non-scale free, a scale-free connection structure. But we have essentially two states, individuals who are protected or who are not protected, represented by not protected and protected. And you have transition uh, continuously between these two compartments. And finally, we have an epidemic layer where the contagion happens, and we have a standard SIR model with infection rates that depends on the protection or not protected states of the individuals. And these are all influenced by the information that spreads in this top layer. So it's a quite elaborate model, and I will try to grab some basic ingredients with you. Um, just briefly, we use a multi-layer networks, and the top layer where they have information, we use a standard bipartite configuration model. You can find the details in this review, but the idea is that you can form a higher order network connecting nodes and edges, in case hyper edges, using different degree distributions. It is a very effective, and you can produce very general networks. While the pairwise networks, we just represent by simple random graphs. In our case, we consider a model that's very standard called a correlated configuration model. Uh, you can find the details in this paper of 20 years ago by Cantazaro and the collaborators. Um, so only to illustrate how important is to consider the higher order interaction here, we're just showing the difference between the spreading process with very similar parameters, very similar contact distributions, but happening on a network with higher order interactions that are these two bottom curves, and on networks with pairwise interaction. Here we have a parameter that is not very important here, that is the threshold above which the information can be spread. Is a kind of complex contagion when you need some minimal amount of activity to spread the information. But you can see clear here that the higher order interaction have a spreading process that is much more effective, much more abrupt than the pairwise spread. This will be important for the epidemic spreading in the other layers. Another feature that I'd like to comment is the importance of the renewal of interest. That is this transition from the Stifler compartment to the uh, ignorant compartment. Actually, if you consider a single, if you doesn't consider the renewal of interest, you have a just quick activity, and then the spreading drop very quickly. And this is not very consistent with reality, because the gossip is renewed because it can be changed. People uh, uh, can restart the interest and spread it again. And then when we include the renewal of interest, you can see that the information stay for longer and longer times in your network. Here I'm comparing different situations. For example, this is a fixed correction rate, but you can look at that the spreaders and also the stiflers, and consequently the corrected individuals change if you consider the renewal of interest. So these two ingredients are important for us. And finally, the cognition part of the model involve simple transitions between the protected and non-protected compartments. Here I have two groups of parameters. One information comes from the information layer that here is represented by the density of gossipers, and the other part comes from the cognition layers that is here connected by the fraction of individuals around you who are protected. And here I have the transition from the protected behavior to the non-protected, and vice versa, from not protected to protected. So these parameters, zeta 1, 2, 3, and 4, are the ones that I'm going to investigate in the next slide. And the epidemic dynamics is very standard. We have
5 more
infection.
minutes.
Okay, thank you. You have infection up to contact and spontaneous healing. So, in this last 5 minutes, I'm going to show you some results that we found. Um, Basically, we can start with a standard epidemic approach and looking for what happened if you neglect the network structure. We can calculate the basic reproduction number and also the control reproduction number that are key epidemic ingredients. Um, Essentially, the control reproduction number are the reproduction number, the number of new infections that happen for when you introduce a new infected individuals, including the control measures. For example, the information spreading or different features. You can see that these numbers are hugely impacted by the cognition layers in the interplay with the information layers. These two results are, if you look for the parameters, they are reciprocal. So one is essentially the mirror of the other, but you can also have the influence of the information layer through this parameter. So the message here is that the epidemic depends on the spread. Um, One key result that I would like to show to you is that if you enhance the protection against misinformation, here I'm comparing the protection against misinformation is this parameter as a function of the protection against your perception of a neighborhood is more efficient to protect against misinformation than against your perception uh, uh, around your neighborhood. So combating misinformation is obviously, as expected, a very efficient strategy. But we can do this in different approach. For example, you can consider this approach when you just suspend people from the network. You identify that there is someone who is spreading some misinformation. You just say, okay, you are not on the network anymore. You cannot spread. Or you can try a different approach. When you meet someone who has spread some misinformation, you try to correct this individual, trying to educate him here. And here we show in these snapshots that it's much more effective to educate individuals than just punish the individual, remove them from the network. So this is a relevant message that we found in our studies. And finally, I will show you only very briefly. Uh, we can alter this model in different ways. For example, here we're considering vaccination as a measure of protection. But now, since vaccines are not reversible, we are vaccinated, we're protected or not. You don't have the two-way approach. And if you apply the model with similar analysis, we observe at least two results that I will show you very briefly. First one is that if you correct individuals, it's effective to increase vaccination, but the impact on the infection on the outbreak size is not too big. So just to educate is not sufficient. Just to correct individuals is not sufficient if you have a higher order spreading of misinformation. But if you start your education program early using the preventive vaccination and the preventive education process, the the process is much more efficient. You can contain this kind of spreading, uh, starting the vaccination program early. So to summarize my my talk, Higher order interactions are important for information spreading and can impact the behavior of individual and consequently the, the type of outbreaks that you have in the epidemic process. To ban spreaders is less effective than educating them. It means that you have to teach people instead of just punishing. And rumor correction is little effective for vaccine effectiveness without preventive actions. And for students, I'd like to show, maybe it's one of the last talks, that complex science is a very evolving field. And this type of investigation, for example, the talk of previous to me, the for Ludovico, that use very advanced tools, you can construct very solid backgrounds and you can do disruptive research in different fields with this kind of stuff. So that's all I have to take. I will let some advertisement here for one event that we're going to organize in 2026 in Viçosa. If you want to know our university, it's a very beautiful place. You have a very famous dulce de leche, milk caramel. You can try if you did not yet. Have very good food, very good nature, and they have also very good cachaça. You are invited to visit us next year. Thank you very much.
Thank you. Thank you for the talk and interesting advertisement for the city and event. We had time for a few questions. So as we see one right away.
Okay, thank you, Professor, for your presentation. I have actually one question about how you model differentiating fake news than just information. Because for me, like many methods that you apply, like okay, the people are spreading information, and the people that are immune, they already know or they are not interested in the just information, but fake news, I think that the model could include something like changes in the initial information or something like that.
Yeah, thank you for the question. The structure of the model you can use to both to investigate misinformation and also support information. You can use the model, for example, to investigate the role of the vaccine campaign. Same way, you can implement this. Let me go back. When you couple this to the infection rates, okay? If you look, for example, in this model, you can see you can couple this here, for example. You can couple this the amount of spreaders. For here, I'm telling that the more dot spreader I have, the less the infection happens. But you can change this. So if you have a misinformation or a good information for your process, you can just change the coupling constants of the model. So it's pretty straightforward to implement. If you look for the, for example, the model that I show for the group from Alex Arenas, they are investigating the opposed. They are looking for warning about the epidemic risk, how it is impacts the infection. So the structures is general. It depends upon the problem that they were investigating.
Okay, thank you.
Okay, we have time for one more question for sure. And depending on the length, maybe a micro question later. Let's see. Let's start one at a time. Zoom, 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 zoom. Aha, Stefano.
So you are using multi-layer network representations in which each layer you have different processes and so on. I don't know, I mean, have you elaborated the possibility of having some compartmental vectorial model instead of multi-layer? That is, each compartment being a vector, and therefore you have a sort of entanglement between the state, aware, unaware, and the state, for example, of the disease. This is something that we did time ago, and I'm just wondering if it can be applied. This we did for consensus dynamics. Sorry, for social epidemics, that is social spreading of technologies and ideas, and not for rumor spreading.
Thank you for the question. Actually, we did not yet, but we are starting touching in this direction in our group. It's not this work; it's a different students that who are working this issue. Is from Viçosa, but we don't have any information to give you right now. But I hope maybe when we met in Siena, I saw that you are invited to talk there. I expect to be there too. We can talk more about this, but now unfortunately I cannot respond to you.
Very good.
So I will cut here the questions. Again, if you have further questions, please do write to Professor Ferreira directly, and I'm sure he will answer. So I have a few things to say, but first of all, let's thank Silvio and Ludovico once more all together. And that concludes this session. Before going to lunch, the lunch break that is going to be now, I want to say once more, please, for those of you who have posters and they are still there, please do make sure that you remove them and the stands are